So today is going to be our fourth introductory lecture and third lecture on measurement and uncertainties. Alright, so I think we should start now. So please be attentive. Excuse me. So we've seen different aspects of the GUM approach, which is the guide to the expression for the uncertainties in measurement. And we've been looking at two kinds of uncertainties. Type B uncertainties are the ones that we dealt with earlier, and they are associated, for example, with single readings. And there is the second kind, which are the type A uncertainties, which are associated with scatter or the statistical description of repeated experiments. So uncertainties that are calculated statistically are called type A uncertainty. And whether you have type A or type B uncertainty, with every reading you would associate a probability distribution function, and you will look at the spread of that distribution function. With the help of that spread, you'll be able to tell what the standard uncertainty is. Right? So with the reading, with the best value, with the probability distribution function, with the confidence that you have in the reading, as well as with the units, you will constitute what is called a proper measurement according to the GUM approach. So we talked about type A uncertainties, and the measure of such an uncertainty is given by the standard deviation or the standard error in the measurement. So we know what the mean is. If we have repeated values, we just sum up the values and divide by the number of experiments that we have to get an average, and the standard deviation is just the deviation of each value from the mean squared. You sum these up, divide by the number of repeated trials that you made, and take the square root. This is the standard deviation, S. But we are really interested in the standard error in the mean, because our mean is the best estimate. So we would like to know what the uncertainty in the mean is, and that is quantified by the standard error in the mean. The standard error in the mean can be calculated from the data. The data gives us S, the standard deviation. From the standard deviation, we can calculate what the standard error in the mean is. And these are the formulas that you will be provided, and you might ask me whether you need to remember these. Well, you repeatedly use these. So any sane, intelligent individual who studies at SSC, by repeated use, he or she will actually memorize these formulas out of practice. So now I would just like to show you two frightening slides, but these are frightening slides at the outset. You can go home and look at the derivation of the three formulas that I've written here. The brave souls can actually repeat these derivations. They're not hard. The notation looks a bit frightening, but let me console you by telling you that this is something within your reach. So here in these two slides, I've given you a derivation of the three formulas that I've presented here. Unfortunately, the 50 minutes that I have, I cannot go through the derivations. So please go to the derivations on your own. So this first slide tells us the relationship between the standard error and the standard error in the mean, and this tells us the relationship between the standard deviation, which is something that comes out of your measurement, and the standard error in the mean. So all of this is nice, simple, juicy mathematics. However, I would like to exemplify this type A uncertainty through an experiment. So what I would like to do is, I would like to take a piece of paper, and I will just make this paper fall from a certain height. And I will repeat the experiment a number of times. So I would like to request a volunteer to come up. Can you please come up? And someone else, I would like to note down the times. I would like you to note down the times. Okay? So what you would like to do, I would like you to do is, I would like you to hold this paper in your hand at a certain height. Let me just show you how to do it first. And this is a stopwatch. You start the stopwatch when you leave this paper, and try to be as repeatable as possible. Okay? So I release this paper, I start the stopwatch, and as soon as it hits the ground, I stop it. And then you speed up these values, 2.56. Okay? So this is how you reset the stopwatch. You practice it once if you like. And just like you will repeat this experiment 10 times. And speak up the value each time. ऊंची बोले? दोबारा? 2.66 seconds. So time seconds. 2.66. अभी दोबारा करेंगे क्योंकि आपसे टकरा गई. In a second trial, and this does not mean that your experiment is better or it's more accurate or it's more precise. You never say this is wrong. This is something I would like to impress upon you. There is nothing right or wrong, and the beauty of experiments is that it becomes a personal affair. You can use your judgment about it. It's unlike your theory classes. You are intimately involved with the experiment. But remember, there is nothing right or wrong. It's just a value that you get. I would like to write down this experiment. What is it? 2 point? It hasn't visibly collided with your body, so just another repeat of the experiment. Why not? These are real experiments that you're performing. One line. Remember, we're trying to find out the spread of these values. So we don't mind outliers, apparent outliers, because anyone else who's going to repeat this experiment will get another spread. All right, thank you very much. Thanks a lot. I think it's just about 6 days, 23 hours, and 50 minutes late, early for the next class. Alright, so this is a series of readings that we obtain. But this is not a measurement, these are just bare readings that we see with our naked eye. So we would like to process this data and we would like to get a measure of the uncertainty. We would like to transform these readings into a proper measurement. Now we've repeated the experiment, so the kind of uncertainty we get is a type A uncertainty. So let's calculate the type A uncertainty associated with this set of readings. So I would like to turn to a calculator, and the calculator that I'm going to use and something that you will use from next week in your class is MATLAB. I'll make a variable. Okay, let me first try to increase the font a little bit. Alright, so I have 10 values of t. Let's call it x. Okay? I have 10 values of x and these are their readings. So can you just pronounce these readings whatever they are? Abu. 2.28. 2.00, 2.19, 2.60, 2.09. Alright, Vinay, is it easy way to increase the font? I tried my best, but Alright. So now what I have here is a set of 10 readings. So I've just taken the 10 readings and put them in a calculator. So I've made a vector of 10 readings. So now I would like to calculate the standard error in the mean. In order to calculate the standard error in the mean, I would first like to calculate the standard deviation S. So how do I calculate the standard deviation is that I take each value and subtract from it the mean. So the mean of this data, mean of the data x is 2.3980. So if I would like to find out the best estimate, it's not the true value, there is no such thing as a true value. The best estimate of my time in the first cut is 2.3980 seconds. Now I'm using many significant figures, two more significant figures than what I'm actually seeing in the reading. But I'm allowed to do that because I have not yet taken the final uncertainty into account. So I use more significant figures in my interim calculations. At the end, I will stick to only the significant figures that really matter. Okay, so I'm doing an interim calculation. I have not yet reached the final quantitative reporting of the result. So I would like to calculate the standard deviation. How do I do that? I take each x and from it I subtract the mean, and then I take the square of each of these values. This is how I take the square of each value in MATLAB, and you learn this next week. And then I take the sum of all of this. And then I divide by the total number of readings, which is 10. 0.0536. So this is the square of the standard deviation. S squared is 0.0536 second squared, right? Because it's a square. So sigma m, the standard error in the mean squared, is given by s squared over n minus 1. And this is a formula, one of the three formulas that I wrote down. So I take this s squared and divide by 9. N minus 1 is 1 less than the total number of readings. So I take this answer and divide by 9. I get 0.0060 as sigma n squared. So I take the square root of this number to get sigma n. Square root of the previous result is 0.0772. So the standard error in the mean, sigma m, which is my uncertainty, and it's of type A, and it's the uncertainty due to the scatter of the results, due to the spread of the results. So the source of uncertainty that I'm repeating this very large number of times, it's a type A uncertainty, and I call it U scatter. U scatter is 0.0072 seconds. Now I'm preserving 3 significant figures here. I'm only allowed to have 2. But I would first like to see if there are other sources of uncertainty. Is there any other source of uncertainty in my using a stopwatch so that I calculate the time for the fall of a patient? Any other source of uncertainty that you think of? Well, air resistance is not a source of uncertainty. Air resistance gives you the actual experimental condition. Height.
Instruments.
Alright, so that's one source of uncertainty, but it's difficult to calculate this in this finite time.
Instruments are uncertain.
The instrument can be uncertain for different reasons. First is the rating or accuracy of this instrument. But stopwatches use a crystal, stopwatches use a crystal quartz oscillator that is good up to 1 part in million, up to microseconds. So the uncertainty associated with these clocks or stopwatches is really small. There's the right. So there is this uncertainty associated with the human reaction. This is a human limitation. It's not necessarily an error or a mistake. We are made in this way. If we are made in this way, we are going to question our own existence. So there is an uncertainty associated with our reaction time. And generally, experimenters have come up with this idea that the response uncertainty is about 200 milliseconds. Okay, roughly. So if you start to stop the watch in one fall, there's an uncertainty of about 400 milliseconds. 0.4 seconds. So this means that associated with this response uncertainty, which is of type B, it's not type A, because this is just a single reading, I can come up with the probability distribution function. By the way, what's the probability distribution function that would give a good depiction of this scatter? It's going to be normal distribution, because I'm repeating this experiment a large number of times. So if I repeat this even a longer number of times, my frequency histogram will approach a bell-shaped curve, or the normal curve, or the Gaussian distribution. However, there is this second uncertainty. Now I can get rid of all of these results because I have the best estimate and I have one kind of uncertainty. For the other kind of uncertainty associated with the human response, I can draw a probability distribution function. That is a uniform probability distribution function that's centered at 0 and goes up to 0.4 on the right hand side and minus 0.4 on the left hand side. So this is the probability distribution function associated with human response, and it's of type B. It's a uniform probability distribution because the uncertainty has uniform probability to lie anywhere in this range. So I use my formula U of, I call it U response. Now this is of type B. This uncertainty were of type A because it's associated with the spread of readings. So I use this probability distribution function. I take half of the integral, which is 0.4, I divide by under root 3, I get some result. I get the uncertainty associated with the response. And I can use my calculator once again. 0.4 divided by square root 3 gives me 0.2309. Second. So now I have two kinds of uncertainties. One of them is type A and the other is type B. And both of these uncertainties are going to contribute. And if I would like to find out the total uncertainty in my best estimate, I would like to add these up in square quadrature. So what I would do, I would take this U response squared plus this U scattered squared and take the under root. And what do I get? I get 772 squared plus 0.2309 squared, and then find out the square root. 0.2435. Now I would like to quote a final result. This is my total uncertainty that has been combined from a type A uncertainty and a type B uncertainty. So using my head, I would like to find out the sources of uncertainty. I would like to tell whether they are type A, type B, associate a probability distribution function with each kind of uncertainty, backbench and talk, and then you would like to add these up to square quadrature to find out the total uncertainty. So the total uncertainty is now 0.2435, and this is your best estimate. So I am erasing everything else from the blackboard. And now I would like to quote a final result. Now the final result, I have two options. The first option is that I just keep one significant figure in the uncertainty. So I only keep this 2. So there's no rounding off that takes place here. This becomes 0.2, and if I just keep this 2, that is one significant figure in the uncertainty, my result would be 2.4 plus minus 0.2 seconds. Alright. The second possibility is, which I would not really follow, is that I would round it up to this point. This becomes 2.40 plus minus 0.24 seconds. This is if I would really like to show off to my instructor that I calculated the uncertainty to 2 significant figures. But this is good enough. 2.4 plus minus 0.2 seconds. Now this uncertainty has crept in from different sources. One is type A, type B. Combine the uncertainties in a proper systematic fashion to find out what the net result is. Now this is your best estimate. These are the units. This is the standard uncertainty, and you're sure that your value, if you repeat the experiment, will lie within this range about 65 to 68% of the times. And if you multiply this by 2, so you have 2.4 plus minus 0.4, then your result will roughly lie in these values 95% of the times. So this is one example of a detailed calculation of standard uncertainty, okay, which combines a type A uncertainty and a type B uncertainty. So let's move on to the presentation now. I have more to say, more examples to present. Alright, just one question. The standard error in the mean is the standard uncertainty. आज कुछ बेकरारी है, क्या पता? थोड़ा सा आगे चले तो करना बहुत पसंद है। किस वाले को जवाब? Alright, so what we have here, we have a type A uncertainty, which is a Gaussian distribution. And if we calculate the standard error in the mean, we know that just for this distribution, there will be a 68% confidence that we have in the range that we've specified. If we have a type B uncertainty, like the reaction time that we've been discussing, then there's a 65% probability, because this is what the second moment of this distribution gives. A 65% probability that if you perform the experiment again, your result will lie in the range specified. Now we have a type A uncertainty which is bell-shaped, and you have a type B uncertainty which is uniform distribution. Now what you're really doing is you're combining the two results. You're combining a bell-shaped curve with a uniform distribution. But if you perform this experiment with a stopwatch that is analog, that perhaps you will get a different uncertainty. So when you quote results, you don't really want to tell you what kind of instrument you use. Your uncertainties should be translatable. They should go from one group to another, from one experimenter to another. You should not really care what equipment you use or what kind of probability distributions you use. So everything is at the end benchmarked against a Gaussian distribution curve. Now this is a slightly subtle point, so I will not belabor this point more than what is absolutely necessary. And in the end, as you've seen, we've calculated the uncertainty to the scatter and to the response, and we've added them in square quadrature. There is also an uncertainty associated with the finite scale of the stopwatch, and that has to be included as well. But when I did my calculation, those uncertainties were really small. But you have to test it out for yourself. So any uncertainty that is really small to the other uncertainties, you don't want to include it in the calculation. It will not contribute to the overall budget of the uncertainty. So you would not like to make your lives difficult, it's already very difficult, by calculating uncertainties that are really meaninglessly small. So you have to use your judgment. Just remember that doing experiments, there's a tinge of personal affection about experiments. It's a personal exercise as well. Two people might not do experiments the same way. They might not come up with the same uncertainty. They might not come up with the same best estimate. So, doing experiments is a kind of reflection of what your personality is. And this is something that I really like about experimental physics. Let's move on. Now, I've already talked about a uniform distribution, triangular distribution, the bell-shaped curve, and I've talked about what the second moments are. In the bell-shaped curve, 68% of the area lies within plus minus 1 standard uncertainty. In the triangular, 65% lies within the plus minus 1 uncertainty. So these values, 65% and 68%, are really the same. So if you calculated the standard error for the standard uncertainty for a triangular distribution, you can easily benchmark it against the Gaussian distribution. And this is something that we are fond of doing. Now let's look at another example. This time we're going to use another device to calculate, or measure rather, the time period of a pendulum. Now what I have here is a simple pendulum, and I have a device that measures the time period of this pendulum optically. So what happens is that when the bob of the pendulum intercepts this gate, there is an LED here and a photodetector here, so it looks at the time of interception or interruption of the infrared pulse, and from that time it calculates the time period. So we're going to use this device, and what I will do, I will oscillate this pendulum in seemingly simple harmonic motion, and I will start this device. So could you please note down the values? 1.3869, 1.3850, 1.3865, 1.3861, 1.3842, 1.3858, 1.3856, 1.3853, 1.3826, कितनी होगी? 1.3851. So once again, we obtained a set of 10 readings using a different instrument. Alright? So now what I would like to do is I would like to calculate the time period of this simple pendulum using this set of data. And I'll get a type A uncertainty, and I might get some type B uncertainties as well. So let's move back to our calculator, which is quite a sophisticated calculator by the way. And can you speak up these values please? So this is our readings once again. Now this is scattered, so I would like to calculate the type A uncertainty. So I take, so the mean of this data is 1.3856. Now look at the number of significant figures that emerge from the reading, 5 significant figures, because it's a more sensitive instrument, not necessarily accurate. It has a better resolution, or is more sensitive. The minimum amount of time that it can measure is very small as compared to normal stopwatch. ये बातें ना करो, ज़रूरी नहीं class में आना. So the best, so I'm going to rub this part of the blackboard. So I start off afresh. So I divide this blackboard into two regions for two sections for reasons that will become clear. My best estimate of the time is 1.3856 seconds. Now I would like to calculate the uncertainty associated with the scatter. It's a type A uncertainty. So what I would do, I would take each value, subtract from it the mean. There are 9 values. Alright, never mind. I will square each one of these values. I will find the sum. I will divide by 9. I will take the square root. This is the standard deviation. S. Right? Now what I would like to do, I would take the square of this, divide by 1 less the number of trials, which is 8, and then I would take the square root of this. These are the three formulas that I wrote. This will give me the standard error in the mean. Now this is a small number. The standard error in the mean, which is really a type A uncertainty, it's due to the scatter. I put an A here to tell you what type of uncertainty is. Remember, when you combine uncertainties, it becomes meaningless what type it is. Originally, it makes sense to have it clear in our mind what type it is. So this uncertainty is 0.000275. So I would like to write 275. I will keep more significant figures than is absolutely necessary in my intended calculations. So this is one kind of uncertainty. There's a Gaussian distribution associated with it, ideally, if I take a large number of readings. Remember, you have to take a sufficiently large number of readings to get meaningful statistics. Now, in this case, there are other kinds of uncertainties as well. Now, there is no response uncertainty, but this instrument itself can be inaccurate. It can have some rating error. For that, we would have to resort to the data sheet provided by the manufacturer of this instrument. So I have a screenshot from the data sheet itself. So generally, one would find a specification sheet for every instrument in its manual or a data sheet on the web. So for this particular instrument, it says that the calculated values are displayed to 1 or 2 decimal places with typical accuracy being plus minus 1 in the least significant digit. So different manufacturers come up with different mechanisms of stating the accuracy. So here the manufacturer states that the least significant digit could be off by plus minus 1. So now there is an uncertainty associated with the rating of this instrument. And that uncertainty is such that I can associate it with a uniform probability distribution with a half length of 0.0001. Okay, this is minus 0.001. Again, this is second, and this is the probability distribution. So now I would like to take half of this interval, that is this interval, divide by under root 3 because it's a uniform probability distribution. I can find the uncertainty associated with the accuracy or rating of this instrument. That will be 0.0001 divided by under root 3 because it's a uniform probability distribution function. Let me calculate this. 0.0001 divided by square root of 3. This is 0.00006. Okay, 4 zeros and a 6. Now this is 3 zeros and a 2. So now if I take the square of this number and I take the square of this number and add them up, this will be an exceedingly small number. So I can just ignore this. This is negligible as compared to this. So when I have different values for the uncertainties, I can just pick and choose. If some source of uncertainty gives you a very small quantitative amount of uncertainty, you just ignore it. You need not perform the calculation. So your total uncertainty will be of this order. And if I would like to keep one significant figure, this becomes 3 because it's at the same position as the least significant digit of the best estimate. So my best estimate for T would become 1.3856 plus minus 0.0003 seconds. So this shows that with the help of this instrument, you can measure incorrect with a precision of up to hundreds of milliseconds. Alright? So this is a proper formal way of calculating uncertainties under the GUM approach. You identify different sources of uncertainty and see what relative contribution does each source give you. Now let's re-perform the same experiment, this time with a stopwatch. A simple stopwatch. So what I would like to do, I would like to set this pendulum in oscillation, and then I would like to find out the time it takes for one period. But it's easier to look at the time for 10 oscillations perhaps. So I just set this into motion. By luck, I just got 13.00 seconds. Alright. So the time that is required for 10 oscillations, I call it T10, is 13.00 seconds as evidenced by the reading that appears on the scale of the stopwatch. Okay? Now there is some uncertainty associated with this. One source of uncertainty again is the response uncertainty. My reaction, my reflex action to starting and stopping the stopwatch. It's 200 milliseconds of starting, 200 milliseconds stopping. So there's a total uncertainty spread of plus minus 0.4 seconds. So I associated with this a uniform probability distribution. This is 0.4, this is minus 0.4, my delta is 0.4. I find the uncertainty associated with my response. It is 0.4 divided by under root 3. Now this is a type B uncertainty. Okay, so what is the result for this? .23 0.231 seconds. Alright. Now we know that this stopwatch is really accurate because it uses a crystal quartz oscillator that has a stability of the order of ppm, parts in millions, of the order of microseconds. So we don't need to worry about the uncertainty associated with the accuracy. Okay? So there is only one major type of uncertainty that we find here. Okay? So now what we would like to do, we would like to calculate the best estimate of the time period. Of course, we have to divide this by 10. So my best estimate for the time period is going to be, oh, there's another source of uncertainty, the finite scale of the stopwatch. Why have we forgotten that? So if we look at the finite scale of the stopwatch, we can associate with it a uniform probability distribution function. So the least count is 0.01. Alright, so you take half of it, this is 0.005. This is minus 0.005. So this U associated with the scale comes out from a uniform probability distribution again. This is this interval, which is 0.005 divided by under root 3. Whatever this value is, it's going to be really small. So I take 0.005 divided by square root of 3. This is 0.003. So this uncertainty is 3 orders or 2 to 3 orders of magnitude smaller than this uncertainty. So this is almost negligible as compared to this uncertainty. So you need to have a good basis of ignoring certain kinds of uncertainties because they are too small. So your best estimate for the time period is going to be this number divided by 10, which is 1.300, with this uncertainty, and you would like to need one significant figure. So your best estimate is 1.3 plus minus point, you have to divide this number by 10 as well, because the uncertainty is going to propagate, and I'll talk about propagation. So this number has to be divided by 10, this becomes 0.02. But if this becomes 0.02, you would like to put in another digit here, because the only digit that is preserved for the uncertainty is at the second position with respect to decimal. So you would like to put in a 0 here, in order everything makes sense. And this is your final result, the final measurement of the time period as calculated by a different device. So now you use two devices, different kinds of uncertainties, type A, type B, and you get two different results. It's the same pendulum, the same length, the length hasn't changed, the time period depends just upon the length, and you get different results. Now which one of these is the true value? This is a bogus question. This question is meaningless. There is no such question as which result is more reliable. You can't say that. Given the conditions, given the apparatus, given the milieu, given what you're operating within, these are the two results, and you've done your full justice to achieve these results. You have best estimates, you have probability distribution functions, and you have uncertainties. अभी मैं आपको जवाब दूंगा, इसके बाद खास वजह से मैं वक्त क्योंकि वक्त बहुत हमारे पास कम है. देखिए, I have uploaded a work example on uncertainty, on a type A uncertainty calculation in the presentation as well, and there are numerous solved problems that are there on the website. You just have to go to the website. On the left hand side there is a link to lab 1, which is physics 200/physics 100. I just updated this half an hour ago. So go to that website, the presentations and all reading material is available on the website. Now I don't have to spoon feed the presentation material or the assistive material, you have to go through it on your own. So this is the best estimate. Now in the last 5 minutes I would like to talk about something really interesting, and this will be a part and parcel of your laboratory course. Suppose I have this rod, it's a simple straight rod, and I ask you to calculate the length of the rod, and I provide you with a measuring instrument, which is the meter rule. Now this is how you would measure it. Now when you take this reading here, you can associate a measurement with this left end, and you can associate a measurement with the right end. Now when I say measurement, it's a combination of the best estimate, the uncertainty, the probability distribution function, the units. All of this is packaged together to give you a measurement. Otherwise, we just have bare readings, which are meaningless. So you have a measurement on the left hand and a measurement on the right hand, and both of these are uncertain. Now you would like to find out the length. Typically, you would calculate the difference between the two best estimates, but that is just a best estimate of the length. What is the uncertainty in the length? Now you have a probability distribution here, and you have a probability distribution here. So now you have two quantities, x and y, and you subtracting these to obtain z, which is the length of the rod. So x is uncertain, y is uncertain. How much is z uncertain by? This is called the propagation of uncertainties. You measure certain basic quantities. For example, you measure the time period. You have a stopwatch, but you don't have a meter read. You want to find the length. Now you have the time period, which is measured by a stopwatch, and from that you would like to measure the length or estimate the length. The time period is uncertain, so would be the length. So how does the uncertainty creep in to the derived quantities from a basic quantity that we measure? This is called the propagation of uncertainty. Propagation का अलग ही मतलब है एक जगह से दूसरी जगह जाना. आपको बेसिक क्वांटिटी मेजर कर रहे हैं, उसके नतीजे में आपको एक derived quantity मिल रही है. ठीक है? Is this not interesting? Or there is something more interesting going on over here? आपको बात करें. Alright, so how do we propagate uncertainties? Now this is a frightening looking formula, but it's not really frightening. So suppose my y is a function of different variables, x1, x2, x3 and x4 up to xn. Like my length of the rod is a function of two variables, x1 and x2. It's this difference of x1 and x2. Okay, so I can have a quantity that depends upon different variables, and each one of these variables is uncertain. So the uncertainty in x1 is ux1, the uncertainty in x2 is ux2, in xn it's uxn. So I would like to calculate the uncertainty in y, given the function. So how I would do it is, I would take the derivative of this function with respect to x1. This is the derivative or the partial derivative multiplied with the uncertainty in x1 and square it. Then I find the derivative of this function with respect to the second variable, multiply to the uncertainty in the second variable, square it, and then I add up all of these terms. And this will be the square of my uncertainty, the final result. Now, how do we come about this? There is a rationale behind this. If I have a function of one variable, just x for example, so y equals x squared, for example. Now this is a graph of y equals x squared, or q equals x squared. Now, there is a best estimate for x best. And there is an uncertainty in x, which is labeled as ux here. Now, I would like to calculate what's the uncertainty in q or y. So, I take this point and I take this point and I find out the vertical stretch of this graph. So, the uncertainty in q will approximately be equal to, if this uncertainty is small, is going to be equal to the slope of this line at the middle point multiplied by the uncertainty in x. This is how we define the slope or the partial derivative. This means that this uncertainty in the dependent variable is the derivative or the slope of the function with respect to the variable times x, times the uncertainty in x. Now if you have different variables x1, x2 and so on, you will just add them up in square quadratic. So the formula that I have written here is just the lowest order term, the so-called Taylor expansion. Last slide or second last slide probably is examples. Now there are plenty of examples that I've uploaded on the website, almost 100 of them. And these are solved examples. And we've written them painstakingly over the years. So go through some of them at least, so that you have a good idea of what I'm talking about. So if I have z equals to x plus y, apply this formula, I get this result. The uncertainty in z squared is the sum of the square of these uncertainties. Z equals x, y, this is the formula that I get. Z equals x over y, this is the formula that I get. I'm just applying the formula that I've written on the previous slide. And this is something that you should derive on your own. These expressions should be on your fingertips. Okay? It's not difficult. For example, if z equals x squared, I take the derivative with respect to x, I get 2x. I multiply this with the uncertainty, I get the uncertainty in z. Yes? You don't get anything? Alright, so go home. From where did you use it? All right, we can talk about this in the office hours. Talk to your peers. Come to me. Of course, it's just 50 minutes and it's a class of 300 students. I'm trying my best, by the way. किसी को कहाँ से समझ नहीं आ रही? डेरिवेटिव्स से आ जाए फिक्र ना करो. All right, it's at this stage. Let me finish by this last half a minute. At this stage, it's important to understand that uncertainties propagate. Okay, you have a basic quantity that you're measuring. There's an uncertainty associated with it, and from this you're deriving some other quantities. So uncertainties will bleed through. They will creep from the basic quantities to the derived quantities. Do you understand this rationale, this philosophy? All right. Now the mechanics is not really important. The mechanics you learn. Go through the work examples. I think you have some problem, fortunately and unfortunately, understanding what derivatives are. Okay? But I'm available, my instructors are available, come to me, we can discuss this right now on the blackboard. Alright, so we'll formally finish the class and I'll see you next Monday. But there's going to be computer laboratory session starting from next Monday. So please check out for your email for that.